So in the last video, our goal was to evaluate some limits algebraically, and in order to do so, we ran into some pretty tricky algebra, but the overall idea was we were trying to evaluate a limit at a point of discontinuity, more specifically at a removable discontinuity. And our strategy for doing so was essentially filling in that open circle that caused the removable discontinuity. And the way you fill in an open circle algebraically is you cancel out this repeated factor, x minus 3 in this case. So in part B, we were taking the limit as x approached 1. We plugged in 1, we got 0 over 0. That told us we had that removable discontinuity. But you may have noticed that there were more than just these two examples on this page. If you scroll down a little bit, you see two more examples of limits that we're going to need to evaluate. And unlike the limits that you see in A and B where we just have quotients of polynomials, in C and D we have some more complicated stuff going on. In C we have this radical function in the numerator, and in D we have this rational function in the numerator. And as you may expect, that's going to make evaluating these limits a little bit more challenging. But the good news is the overall strategy that we employed in A and B is still going to work on C and D. Let me demonstrate. Suppose we're trying to take the limit as x approaches negative 7 of this expression. I wouldn't ask you to take the limit of a function at a point of continuity, so you can't just evaluate this limit by plugging in negative 7. But even though you're pretty sure that's not going to work, it's not a bad idea to plug in that negative 7 anyways and see what happens. If I change all the x's into negative 7s, I get the square root of negative 7 plus 11 minus 2 up in the numerator. And down in the denominator, I would have negative 7 plus 7. In the denominator, I clearly have 0, negative 7 plus 7. In the numerator, negative 7 plus 11 is 4, and the square root of 4 is 2. So I have 2 minus 2, I get another 0. Much like we saw in the previous examples, when we try to evaluate the limit by evaluating the function at that point, we get this undefined output 0 over 0. That's bad news and good news. It's bad news because it doesn't immediately give us the answer, but it's good news because it gives us a lot of information about these functions. The fact that the denominator evaluates to 0 tells us that negative 7 is a root of the denominator. Well, yeah, obviously it is. The only number that's going to make the bottom equal to 0 is negative 7. Right, but maybe a little bit more surprisingly, negative 7 is also a root of the numerator. When you put negative 7 into the top, 0 comes out. If negative 7 is a root, that means x plus 7 must be a factor. What I'm saying is there's an x plus 7 hidden in the top and hidden in the bottom. In the bottom, it's not hidden very well. It's kind of in plain sight. There's the x plus 7 right there. But there's an x plus 7 in the top that's very well hidden. It might be surprising to you that there's an x plus 7 up here. But there has to be an x plus 7 up here because negative 7 is a root of the function. And again, negative 7 is a root of the function because when I evaluate the top at negative 7, 0 comes out. So all I have to do is find that x plus 7 so I can cancel it out with this x plus 7 to fill in the hole, the removable discontinuity that I know exists because of this output, and that will leave me with a function that's continuous at negative 7, so it'll be much easier to evaluate. So that begs the question, how do you find the hidden x plus 7 in the numerator? Well, there's a trick, but the good news is it's a trick that you've seen before. In the previous section, when we had radical functions, meaning variables underneath the square root sign, we had a method for getting rid of that square root. It was called multiplying by the conjugate. That's exactly what we're going to do here. In the numerator, I have two terms. The first term is the square root of x plus 11. The second term is this 2 right here. In between those two terms, I have a negative sign. If I want to write the conjugate, I write those exact same two terms, but I change the sign in between the terms. So I'm going to switch this negative to a positive right here. The trick for locating the x plus 7 in the numerator is getting rid of this square root sign. The trick for getting rid of the square root sign is multiplying by the conjugate. And maybe you're like, wait a minute, you can just do that? You can just multiply by something? Well, kind of. I can multiply the top by this thing as long as I also multiply the bottom by this thing. As long as I multiply the top and the bottom by the same thing, you can kind of just think about it like I'm multiplying this fraction by 1. Everything that I just wrote in blue here is just a fancy form of the number 1. So when I multiply by 1, I don't change the value. And you're like, wow, this problem got really ugly all of a sudden. Well, kind of. But if you learned anything in the last section about multiplying by the conjugate, you might know that in the next step, things are going to simplify very nicely. In the top, I'm multiplying something with two terms times something else with two terms. So think that acronym FOIL. I got to multiply these two terms together, and then I got to multiply these two terms together, and then these two terms, and then finally these two terms. So I take the square root of x plus 11 and I multiply it by the square root of x plus 11. When I'm multiplying something by itself, I'm squaring that thing. So I'm squaring the square root of x plus 11. The square and the square root cancel out, and I'm left with just x plus 11. That's the f in FOIL. For the o in FOIL, I'm going to multiply together this term, the square root of x plus 11, and this positive 2 right here, which gives me 2 times the square root of x plus 11. For the I in FOIL, I'm going to multiply this negative 2 and this square root of x plus 11, and that gives me negative 2 times the square root of x plus 11. And then finally, the L in FOIL is this negative 2 times this positive 2, which gives me negative 4. I thought you said this was going to simplify really nicely. Yeah, it does. Just like we saw in the previous section when we multiplied something by its conjugate, the O and the I in FOIL are almost the exact same, just one is positive and one is negative. Oh yeah, that makes sense. The two terms that I write here are the exact same as the two terms that I write here, except that I've changed this sign. So this number is the opposite of this number. Therefore, the O and the I in FOIL are going to be the exact same thing, except one of them is going to be negative and one of them is going to be positive. What I'm saying is this and this cancel out, and so the numerator is a lot cleaner than you might think. What about the denominator? Well, if you really want, you could FOIL out the denominator, but I would not recommend it because remember, our goal is to get rid of this x plus 7. We're hunting for the x plus 7 in the numerator so we can cancel it with this x plus 7 in the denominator. If you go FOILing out the bottom, you'll lose this x plus 7 and you'll have to go hunting for it again. Don't go losing the thing you're trying to get rid of. Keep this x plus 7 by itself. Leave the denominator as x plus 7 times the square root of x plus 11 plus 2. What I'm going to do now is combine like terms, and as I've already mentioned, this term and this term are going to cancel each other out. So what will I have left up on the top? Well, I guess I'd still have this x right here, and then if I'm looking for my constants, I'd have 11 here and negative 4 over here. So I'd have to add up 11 and negative 4. Let's see, 11 plus negative 4. I guess that's 7. Oh wow, look at that, x plus 7. Kind of cool, right? The numerator simplifies to exactly x plus 7, which I also have in the denominator, x plus 7. That's going to allow me to cancel stuff in the very next step. And you're like, yeah, whatever, good job. You made some problem work out really nicely by choosing the numbers really carefully. No, I didn't. In any problem that kind of sets up like this, where we're evaluating a limit at a removable point of discontinuity, if there's a radical function either in the numerator or in the denominator, it has to pop out after you get rid of the radicals. And the way you're going to get rid of the radicals is by employing this conjugate trick. The fact that this x plus 7 showed up right here was not a coincidence and had nothing to do with me reverse engineering some problem to make it work out really nicely. It's always going to be the case. I now have the satisfying step of canceling out this x plus 7 and this x plus 7 to get the limit as x approaches negative 7 of 1 divided by the square root of x plus 11 plus 2. Couple of comments. What you see inside this red box right here is not the same as what you see inside this pink box right here. If you watched the last video, I might be sounding like a broken record. These are not the same. In order for expressions to be the same, they have to be the exact same when evaluated at any value of x. And this, when you evaluate it at negative 7, is not the same as this when you evaluate it at negative 7. However, that does not nullify this equal sign. This equal sign here is legit because I'm writing the limit as x approaches negative 7 of these expressions. And these expressions, as I approach negative 7, are the exact same. The limit as x approaches negative 7 of this expression, that's really easy to evaluate because this expression is continuous at negative 7. I change all the x's into negative 7s, and I get 1 divided by the square root of negative 7 plus 11, aka 4, plus 2. The square root of 4 is 2. 2 plus 2 is 4. I get 1 over 4 as my limit. For the visual learner out there, I want to show you a little bit more about what's going on. So consider this original expression as a function, the square root of x plus 11 minus 2 divided by x plus 7. It's what I have written right here, and it's what shows up graphed right here. What we're trying to do is evaluate the limit of this thing as we approach negative 7. You might be like, wait a minute, that's weird. In the graph, it looks like it's continuous, but I thought you told me that there was a removable discontinuity at negative 7. In fact, there is a removable discontinuity at negative 7. It just doesn't show up with this graphing software. Look what happens when I move over to negative 7. It knows that at negative 7, the function is undefined. It gives me that open circle when I hover over it, but for whatever reason, when I'm not right on top of it, it doesn't show me it. So first of all, there is an open circle at negative 7, even if there doesn't appear to be. What is the height of that open circle? Well, it's kind of hard to tell, but if 1 is right here and 1/2 is right here, maybe you would buy that the height of this open circle right here is 1/4. Another way you can justify that is look, if we're just a little bit off, looks like we're really close to 1/4 on either side. Over here, we're a little less than 0.25. Over here, we're a little bit more than 0.25. And there's the point of discontinuity at -7. Another comment. This is not the only discontinuity of this graph. The graph stops over here at -11. There's nothing further left of -11. What's going on there? That's something completely different. That's because I can't take the square root of a negative number if I'm dealing with real numbers. And if x is further negative than -11, like -12, for example, -12 plus 11 would be -1, and I'd be taking the square root of a negative. So that's why the graph stops right here. Not really related to our limit, I just wanted to make the comment. The other comment that I want to make is, what I have written right below here, 1 over the square root of x plus 11 plus 2, is what we have down here. I claim that this expression is not the same as this original expression, but it's very similar. This graph is supposed to be identical to this graph with one difference. This graph does not have that removable discontinuity at -7. This graph is continuous at -7, which is what makes it so easy to evaluate this limit. Let's see if the graph confirms that. Instead of looking at this graph in red, the original function, I want to look at this graph in green. But note that it looks really similar. There's green, there's red. Looks like they line up right on top of each other. They look identical. But remember, the red graph, when I look at -7 right here, has an open circle. When I switch over to the green graph and go back to that point at -7, there's no open circle. The circle's closed. The circle has a height of 1/4. Red and green are almost identical. Red just has the removable discontinuity, and by algebraically changing red into green, I've filled in that open circle, which makes my function continuous at -7, which makes it really easy to evaluate the limit. You want to evaluate the limit of this thing? Just change all the x's to -7s. In other words, ask the graph how high up it is at -7 right here. The answer is that 0.25 you see in front of you. You can't do that same thing with the red graph because the red graph has that open circle at -7. So you can't ask it what its height is at -7. It's undefined. Maybe I'm beating this to death, but I really want you to understand the mechanics of what's going on with all this algebra, because it's so easy to get lost in all these different tricks and all this manipulation and not really understand what you're doing. But I think the most interesting part is understanding the mechanics of what you're doing. Anyways, let's move on to the last example in this video. Part D here looks like a mess. It looks super complicated, but it'll turn out that it's kind of similar to a problem we've already done and really isn't any harder than any of the stuff we've done above. We're evaluating a limit, specifically the limit as x approaches 6 of this huge mess. Now, we don't have quotients of polynomials like we did in A and B, nor do we have a radical function in the numerator like we did in C. We have a rational function. We have the kind of fractions inside fractions case that we saw in the previous video. First thing you probably want to check. I wonder if he was nice enough to give me a continuous function here, and I can just evaluate this limit by changing all the x's into 6's. You know that's not going to work, but you should still try it. Let's change all the x's into 6's. I'd get 6 plus 1 divided by 6 minus 5 minus 7 divided by 6 squared minus 36. Let's see, 6 plus 1 is 7, and 6 minus 5 is 1. So I get 7 over 1 minus 7. I get 7 minus 7 up on the top. And 6 squared is 36, so I get 36 minus 36 on the bottom. Looks like I get 0 over 0, just like I got 0 over 0 up here, and I got 0 over 0 up here, and I got 0 over 0 up here. It's not a coincidence. That's always going to happen when we have these removable discontinuities, which is the case we're most interested in. Because I got 0 over 0 right here, which is an undefined output, I can't evaluate this limit by just plugging it in 6's. This graph is not continuous at 6. Don't believe me? Let's go over to Desmos here. I've typed in the graph right here, x plus 1 divided by x minus 5 minus 7 over x squared minus 36. Let's take a look. Here's the graph, kind of complicated looking. Remember, we're evaluating the limit as x approaches 6. So let's come over here to 6. Oh, it sure looks like it's continuous. Let's just click on the graph right here and figure out what the height is at 6. Ah, bummer, it's undefined. There's an open circle there at 6. It just didn't show up immediately with this graphing program. I mean, yeah, since I have the graph, I can look a little bit to the left and a little bit to the right, and I can kind of tell it looks like we're hovering really close to -1/2. I bet the answer is going to end up being -1/2, but if we didn't have the graph, we wouldn't be able to figure that out. Algebraically, all we can see is the open circle at x equals 6. We have no idea what the y coordinate of that open circle is. So what do? We take advantage of the fact that because plugging in 6 made the bottom 0, there must be an x minus 6 hidden in the bottom. And because plugging in 6 made the top equal 0, there must be an x minus 6 up in the top. 6 is a root of the function in the denominator, so x minus 6 is a factor. 6 is a root of the function in the numerator, so x minus 6 is a factor. One of those x minus 6's is pretty damn easy to find. X squared minus 36 is what's called a difference of squares, and it factors really nicely. It factors as x plus 6 times x minus 6. Hey, there's that x minus 6 I was talking about. If I could just find the x minus 6 up in the numerator, I'd be good. I'd cancel out those x minus 6's, essentially filling in the open circle. This graph would then be continuous at 6, and it'd be really easy to evaluate this limit. Unfortunately, the x minus 6 is hidden pretty well up in the numerator. It's tempting to be like, plus 1 minus 7, that gives me x minus 6, kinda, sorta. Nah, that algebra doesn't work. What we instead have to do is employ the exact same trick that we went over in the previous video when we saw rational functions. I want to make this entire mess a fraction divided by a fraction. The denominator is really easy to make a fraction. I can just divide it by 1. The numerator is a little bit harder to make a fraction because I have a difference of two things. Right now it's a difference of a fraction and a whole number. So the first thing that I'm going to do is change that whole number into a fraction. I'm going to write this as x plus 1 over x minus 5 minus, and then instead of writing 7, I'm going to write 7 over 1. That's closer to a fraction over a fraction. The bottom is all one fraction, but the top is a difference in two fractions. So I want to subtract those two fractions to make them a single fraction. How do I do that? Well, if I'm trying to subtract fractions, I need a common denominator. The least common denominator between x minus 5 and 1 is just x minus 5, which I can create by multiplying the top and the bottom over here by x minus 5. It's important that I multiply the top and the bottom by the same thing, kind of like I did up here, so that I'm not changing the value of anything. Things are getting pretty ugly over here. Hopefully it's going to clean up really nicely in this next step. Let's see. I have x minus 5 here and 1 times x minus 5. In other words, x minus 5 here. I have a common denominator. That means I can subtract these two fractions. The way I subtract fractions is I write their denominator one time. There's that x minus 5. And then I subtract their numerators. The example that I gave last time is think 6 sevenths minus 2 sevenths equals 4 sevenths. You only write the 7 a single time and you subtract the 2 from the 6 to get the 4. I only write the x minus 5 a single time and I take x plus 1 and subtract 7 times x minus 5. I better do that in the next step. There's the x plus 1. From that I want to subtract 7 times x minus 5. Nothing that I need to do in the denominator. I'll just leave that as x plus 6 times x minus 6 divided by 1. I've already found my x minus 6 that I'm trying to get rid of, so I don't want to do anything over here. Maybe before I go any further, I can clean up the numerator a little bit here. If I take this negative 7 and distribute it through the parentheses, I'd have negative 7x. But I also have positive 1x over here. So I have positive 1x minus 7x. It sounds like in total I have negative 6x. And then when I take the negative 7 times the negative 5, I get positive 35. But it's not just that positive 35, there's also this plus 1 right here. So in total I have positive 36. The numerator can be simplified to negative 6x plus 36, and that's divided by x minus 5. And then the denominator, I'm going to leave it completely alone. I still have x plus 6 times x minus 6 divided by 1. And what I'm trying to do is take the limit as x approaches 6 of that entire expression. I now have a fraction divided by a fraction, so I could divide these fractions by changing it to multiplication and flipping the bottom upside down, multiplying by the reciprocal of the denominator, but I'm going to wait one more step to do that. Because remember, my whole purpose is to get rid of this x minus 6. There was supposed to be an x minus 6 up in the top and an x minus 6 down in the bottom. I found the x minus 6 down in the bottom, it's right here. But where's the x minus 6 up in the top? X minus 5, really close. Nah, that ain't it. It's up in here. Negative 6x plus 36. Look what happens when you factor out a negative 6 from each of those terms. If you pull out a negative 6 from negative 6x, you're left with just x. If you pull out a negative 6 from positive 36, you're left with minus 6. There's that x minus 6 that was hidden so well that I've been looking for the whole time. I'm going to leave everything else completely alone because I'm now ready to switch this from the division of fractions into the multiplication of fractions by taking the fraction down on the bottom and flipping it upside down. This limit is the same as the limit as x approaches 6 of negative 6 times x minus 6 divided by x minus 5. And then instead of divided by, I'm going to make it times. And if I switch from division to multiplication, I have to take the reciprocal of this thing. So I'm going to make it 1 over x plus 6 times x minus 6. Look at what we have here. Negative 6 times x minus 6 times 1 on the top. And x minus 5 times x plus 6 times x minus 6 down on the bottom. I have this common factor of x minus 6 that I can cancel out. If I cancel out those x minus 6's, I get the limit as x approaches 6 of negative 6 over x minus 5 times x plus 6. Right, this is gone, so negative 6 times 1 gives me this negative 6, and this is gone, so I got x minus 5 times x plus 6. You can probably guess what I'm going to do next. This expression right here is not the same as this expression right here, but they're very similar. The only difference between the two is that I've canceled out these x minus 6's. Essentially, I filled in that open hole that I had at x equals 6. Everything else is the same. Because everything else is the same, the limit of this red box as x approaches 6 is the same as the limit of this green box as x approaches 6. And the nice thing about the limit of this green box as x approaches 6 is it's something that I can evaluate because the green box is continuous at x equals 6. All I gotta do is change all my x's into 6's. I get negative 6 divided by 6 minus 5 times 6 plus 6, which is negative 6 divided by 1 times 12, which is negative 6 divided by 12. In other words, negative 1/2. Oh yeah, that's exactly what I was expecting to get when I look at my graph over here in Desmos. At x equals 6, I have this open circle, but just by looking at the graph, I can tell that my height when I get really close to this open circle is really close to negative 1/2. However, I don't have that luxury when I'm doing things completely algebraically. So in order to tell that that open circle has a height of negative 1/2, I have to fill in that open circle, and that's what I'm doing going from this line to this line. That's some pretty complicated algebra, but the good news is the tricks that we did in this video are the same tricks that we did in the last section. Multiplying by the conjugate to get rid of the square root sign, and manipulating things so that you have a fraction over a fraction, and multiplying by the reciprocal to get rid of fractions inside fractions. They're the same tricks that we did last time, and it'll turn out they're the same tricks that we're going to see in the next section.